We're going to be introducing here some probability rules. And before we do that, we're going to try and create some diagrams that will actually help us visualize what probabilities are. Well, this diagram is called a Venn diagram because it's a useful way to view events and outcomes. It consists very simply of a sample space S, which is represented by this blue region, and a circle representing a subset of outcomes, in this case A. The diagram below says that a subset of outcome A is a subset of the entire sample space S. For example, rolling a 1 on a dice is a subset of the entire sample space S for all possible outcomes on that dice. And so the circle A is embedded within this S or sample space. Let's look at the first rule. The first rule is the complement rule, and it is the opposite of an event occurring. Given 3 cards labeled A, B, and C, if the probability of A being selected is 1/3, then the complement, or the probability of A not occurring, would be 1 minus 1/3, or 2/3. Mathematically, this is denoted as the probability of A equals 1/3. Therefore, the probability of the complement, which is denoted by this bar over the letter A, so this is read as the probability of the complement of A, is equal to 1 minus the probability of A, which is 1 minus 1/3, or 2/3. Thus, the probability of choosing not A, which means it's going to be B or C, is 2/3. In a Venn diagram, the complement rule is the opposite of the subset of the outcome set. So the blue space, remember, is S. That's our full sample. And A represents the subset that we were looking at. Therefore, the rest of the blue space without the A is known as a complement, or not A. Now let's look at an addition rule. The addition rule provides the probability of independent events occurring. For example, assume on a regular dice with 6 sides, it's fair. The probability of any number coming up is 1/6. So the probability of rolling a 1 or a 2 is the probability of each occurring. So we'll denote this mathematically as follows. The probability of 1 is 1/6. The probability of 2 is 1/6. So the probability of rolling a 1 or a 2 is the probability of a 1 plus the probability of a 2. 1/6 plus 1/6 is equal to 2/6, which is equal to 1/3. Using a Venn diagram, the addition rule is called the union of 2 sets. In the previous example, the event A of rolling 1 and event B of rolling 2 were combined to assess the probability of rolling a 1 or a 2. So we have 2 different sets here. We have A and B. And there's no intersection. You're going to notice they're completely separate, and it's only just by the diagram being drawn that they kind of touch each other. So that has nothing to do specifically with this example. But it shows the event A and event B in that complete gray region. And so the union is basically the probability of A union with the probability of B, such that you add them together. In the multiplication rule, assume we have 2 independent events, such as 2 rolls of the dice. So we're using 2 dice now, whereas before we used 1. But an analyst wants to examine the combination of events, such as rolling the probability of a 1 and the probability of rolling a 2 on 2 separate dice. In this case, the probabilities are multiplied. So we have the probability of A and the probability of B. We're going to multiply them together. Now here you have the probability of 1 is 1/6, the probability of 2 is 1/6 as we've shown before. But since we're saying the probability of rolling a 1 and a 2, we would take 1/6 times 1/6, which equals 1/36. Another way to look at this would be you have 36 events on the dice. So if you consider all of those, where you have 1, 1, 1, 2, 1, 3, 1, 4, all the way down to 6 and 6, we're saying what is the probability of rolling a 1 and then rolling a 2? So that specific combination is a 1 and then a 2, and it will only occur once out of the 36 possible events. Now, let's take a little bit closer look here. Consider the problems where 2 outcomes might have some overlap, such as rolling a 3 on a dice and have an even sum on the dice. Below are two tables to show all possible outcomes. So here's all the outcomes of two sets of dice. The yellow represents one dice, the blue represents the other dice. There are 11 possibilities for the left table, which is that a 3 is rolled, and 18 possibilities for the right table, in which the outcome is even. The overlap, or green, between the two sets is what we're looking for. Using simple addition, the number of outcomes would be overestimated. If we did simple addition, we would have the 11 and the 18, which is too much. But if we count the greens only once, the total number of outcomes are 24 out of 36 possible combinations. And this overlap is called the intersection of the two, which is the probability of A intersect B. In this case, the calculation could be represented as follows. Probability of A is 11 out of 36, and the probability of B is 18 out of 36. So the probability of A intersect B is going to be 5 out of 36, and here's why. The addition rule is more formally written as this. The probability of A union B is the probability of A plus the probability of B minus the probability of A intersect B. So if there is any overlap, I don't want to count them twice. And that's what we're doing here with the addition rule. We're subtracting that set that basically causes this intersection. So we have 11 out of 36 plus 18 out of 36, and we're subtracting 5 out of 36, which gives us 24 out of 36. Looking at the Venn diagram, the equation for this union, if there is overlap, shows that we just need to subtract that intersection part because it's already going to be counted as part of the other one. It's some excess. And so that's what we're doing. We're subtracting the blue region, not because we're eliminating it completely, but because it's being double counted. In the case where there is no intersection between the events are said to be mutually exclusive. In this case, the Venn diagram is represented as two circles with no intersection, and the formula for that intersection would have a 0. As we can see below, here we have the probability of A plus the probability of B minus the intersection, which in this case is 0, which just gives us the probability of A plus the probability of B. And this is similar to the dice example that we had when we started this.